So in the next session, that is session number 3 about haloalkanes, haloarenes, now we are going to discuss about the preparation of haloalkanes. From now I will be discussing only about haloalkanes, its preparation, its properties, and as well as your chemical properties and physical properties of haloalkanes, followed by separately we will be taking your haloarenes. Nomenclature and your CX bond nature we have taken it together, that is your haloalkanes and haloarenes. From now we are going to discuss only about the haloalkanes first, followed by your haloarenes. So haloalkanes can be majorly prepared from the starting materials as alcohols, your hydrocarbons, as well as through your halogen exchange reactions. So these are the 3 main methods wherein you can prepare your haloalkanes. So let us see a flow chart which tells you about preparation of haloalkanes from all these 3 starting compounds, followed by one we will be going to discuss about the details. So this is the complete picture of complete flow chart which shows you that how many different methods of your haloalkanes preparation is there for your syllabus. So this is the complete picture wherein you can see all types of preparation of haloalkanes. Before going to explain your preparation of haloalkanes, I want to do you something, that is, there are lot of named reactions as well as there are 4 to 5 mechanisms that will be studied in your organic chemistry. So what should you do is note down all the named reactions. See this Sand-Meyers reaction, Darzin's process, Finkelstein reaction, Schwarz reaction, all these are called as named reactions, that is they are named with respect to the scientists who have put forth this preparation or put forth this reaction. So all these named reaction, do a list of these named reaction. It will be about 32 named reactions all along your haloalkanes, alcohols, phenols, aldehydes. So completely organic chemistry if you take it, you will be getting 32 to 33 named reactions which will be helpful if you list it in one page. So if you are taking a book for this organic chemistry, in the last page of the book, make a note of all the named reactions plus 4 to 5 mechanisms that will be there for your board level. There are 4 to 5 mechanisms that is asked for your board level. So 4 mechanisms plus all the named reactions, either it is haloalkanes, haloarenes or your amines. Anything, make a list of these named reactions. So it will be helpful at the end of the year to get all the named reactions at one page. Even myself, get prepared for your organic chemistry classes. Every day I will be getting ready, I will be writing the reactions and then coming to your class. That means that without preparation, without having daily practice, you cannot write your organic reactions very easily. So daily practice is needed for your organic chemistry very importantly. That is, at least write two reactions per day. So it will be helpful for your end of your board exams. So as I have already told you, preparation of haloalkanes is majorly from 3 compounds, 3 types of reactions. So the first one is from alcohols. Preparation is from alcohols. Alcohol is the starting material wherein you can prepare your haloalkanes, get your haloalkanes from alcohols. There are 3 methods in which you have to, you can react your alcohols and get your haloalkanes. That is first one is from Lucas reagent. It is also called as Groove's process. It is also called as Groove's process wherein you use your HCl or HX as your reagent. So it's your Lucas reagent. More about Lucas reagent, you will be coming across it in your alcohols also. But here also we will be seeing about Lucas reagent. So it is from Lucas reagent. It is also called as Groove's process. The next one is from your phosphorus halides, phosphorus pentahalides as well as phosphorus trihalides. The last one from your alcohols is from Darzin's process. So these 3 are the methods, only 3 methods wherein you convert your alcohols into haloalkanes. Next one is your hydrocarbons. From your hydrocarbons, either it is alkane, alkene or alkyne. It is generally called as the hydrocarbons. Hydrocarbon is your starting material. There are 4 methods from which you are preparing your haloalkanes from your hydrocarbons. First one is your free radical halogenation. It is present in your first PUC also. Hydrocarbons chapter li idide free radical halogenation anta. Electrophilic substitution reaction. Electrophilic substitution reaction. Idu ide halogenation anta. So electrophilic substitution reaction. Idu first year alli ide. Next from alkenes. It is from alkenes. Idu ide nimma first PUC li. Then followed by Sand-Meyers reaction. So Sand-Meyers reaction, it's a named reaction, very important reaction, Sand-Meyers reaction. A special type of reaction wherein you prepare haloalkanes, especially your fluoroalkanes and iodoalkanes. through halogen exchange reaction. I will be telling in detail what it is. There are two named reaction, two halogen exchange reaction, very important for your board level. One is Finkelstein reaction, the other one is Schwarz reaction. So totally Lucas reagent, that is your Groves process, Darzin's process, Sandmeier's reaction, Finkelstein and Schwarz reaction. There are 5 named reaction in your preparation of haloalkanes which you have to put a note on your last page of this notes book. Okay, take a note of these flow chart. It will be very helpful rather than getting into each and every reaction and scratching your head at last. So flow charts in your organic chemistry will be very helpful for your board exams. So as I have already told you from alcohols there are 3 methods. So I will be taking a flow chart even for your alcohols. So I will be taking a general example as ROH alcohol. R can be any alkyl group. If you have a board question, if they have given R, what is R? Respective R can be substituted. As I have told you, there are 3 methods of preparation, 3 methods. The first method is from Lucas reagent. So what is Lucas reagent? It's nothing but anhydrous zinc chloride plus concentrated HCl. Concentrated HCl. It is called as Lucas reagent. You get your RCl from that respectively. Haloalkane, you get your respective haloalkane. Anhydrous zinc chloride concentrated HCl. Remember, it's called as Lucas reagent and this reaction is called as Groves process. Very important. Even your Lucas reagent is also very important. In detail, we'll be studying about this. This is just a flow chart of your preparation of haloalkanes from your alcohols. The next method, it is from phosphorus pentahalides or phosphorus trihalides. You get your respective haloalkane. It can be either PCl5, PCl3, PBr3 or PI3, anything for that matter. You get your respective haloalkane. So that's your second method. And the third method is from Darzin's process. The reagent is thionyl chloride in presence of pyridine. It's an organic base. I'll be telling what is the importance of that. And the name is Darzin's process. You get your RCl, your alloalkane, that is your chloroalkanes is obtained. So Darzin's process. So these are the 3 main methods wherein you convert your alcohol into your haloalkanes. So if you have an option of which of the following converts your alcohol into haloalkane. So which are the reagents which has the capacity to convert your haloalkane into your, that is your alcohol into haloalkane is anhydrous zinc chloride followed by concentrated HCl, any phosphorus halide followed by your thionyl chloride in presence of pyridine. So these are the 3 reagents which are capable of converting your alcohol into your haloalkane. So one by one we will be discussing in detail. First we will be taking your Groves process, that is I will be taking an example here. I will be not taking your general example. So first method, that is your Groves process. So this is your alcohol, it's a tertiary alcohol. So what do you mean by a tertiary alcohol? OH group is attached to a tertiary carbon atom. They are called as tertiary alcohols. So this is a tertiary alcohol. Add your anhydrous zinc chloride in presence of concentrated HCl. What do you call this combination as? It's called as Lucas reagent. You get your haloalkane. So this is the method wherein Groves process, wherein you use your Lucas reagent to convert your alcohol into chloroalkanes. You get your chloroalkanes. The reactivity order of this reaction, that is Groves process, what is the reactivity order for alcohols? If I take the reactivity order for alcohols, tertiary alcohols are more reactive than secondary than primary alcohols. What do you mean by secondary alcohol? If your OH group is attached to a secondary carbon, they are called as secondary alcohols. What do you mean by primary alcohols? If a OH group is attached to a primary carbon atom, it is called as your primary alcohol. So what happens to the alcohols, types of alcohols when they react with anhydrous zinc chloride and concentrated HCl is tertiary alcohols react very rapidly, secondary alcohols react a little bit slower, primary alcohols neither they do not react or react upon heating. So this is the reactivity order with respect to your alcohols. What type of reaction do they give with your Lucas reagent? Remember, this is your Lucas reagent 1 mark question. What is the composition of your Lucas reagent? It's a common question asked in your board level. Whether you can use only concentrated HCl or whether you get only chloroalkanes. If that is the question, no. You can also use HBr, You can also use your HI, that is hydrobromic acid, hydroiodic acid also in the Groves process to get your respective bromoalkane as well as iodoalkane. So in your Groves process, as I have told you, you can only prepare your haloalkane, that is chloroalkane, since your reagent is concentrated HCl. So instead of concentrated HCl, why can't we use a HBr, hydrobromic acid, as well as hydroiodic acid to get the respective bromoalkanes as well as your iodoalkane. So what is the method? If you see, we have prepared ethyl bromide, that is nothing but your bromoethane. So the method, if you observe, it is CH3CH2OH alcohol reacts with sodium bromide as well as sulfuric acid to give your respective bromoalkane, that's your ethyl bromide or bromoethane. So where is the hydrogen bromide, that is hydrobromic acid? If you have a question, these reagents which I have used has a reaction between themselves as like this. Itara reaction agi, that is sodium bromide reacts with sulfuric acid to produce your hydrobromic acid in situ. You call this as in situ preparation. A very important word, in situ preparation. What do you mean by in situ? In situation. What is the situation? This is the reaction situation where you have taken these two reagents. They react inside the reaction mixture itself to produce this hydrobromic acid. This hydrobromic acid produced in situ will react with this alcohol to get back your bromoalkane. So this hydrogen bromide is unstable. It is not stable like your HCl, so that we can prepare it and we can keep it in a bottle which you see in your laboratory. It is very unstable. Hence, this is not prepared and added externally. This is prepared in situ, and this HBr which is prepared in situ reacts with your alcohol to get your bromoalkane. So this is called as in situ preparation. Why it is in situ prepared? That is because you cannot prepare at a lab temperature and store it in a bottle as we do for your HCl. HCl is a gas. You saturate with the water and you get your HCl acid, hydrochloric acid. But hydrobromic acid, it's not so stable as your HCl to get prepared and keep it in your bottles. Hence, HBr is prepared in situ by reacting with your sodium bromide and sulfuric acid. In the same way, if you come into your next haloalkane, that is iodoalkane, that is prepared here, you can observe your alcohol reacts with potassium iodide as well as phosphoric acid. H3PPO4 is your phosphoric acid. You get your iodoalkane as the main product. Again, illu niಮಗೆ question barbodu, where is the hydroiodic acid? Again, the same explanation for your this reaction also. Your hydroiodic acid is still unstable than your hydrobromic acid. Hence, it is not prepared and stored and not put externally into your reaction mixture. That is HI, hydroiodic acid, is also prepared in situ. Your potassium iodide as well as phosphoric acid react to produce this hydroiodic acid inside the reaction mixture itself. This hydrogen iodide prepared inside the reaction mixture reacts with your alcohol to give your iodoalkanes. So this is how you react your hydrobromic acid as well as hydroiodic acid in situ to get your iodoalkanes and bromoalkanes respectively. Just like your HCl, you cannot add your hydrobromic acid, neither your hydroiodic acid externally, just we do in your Groves process. So hence, these two, hydrobromic acid as well as hydroiodic acid, are prepared in situ. The other thing, here we have used H2SO4, here we have used phosphoric acid, a milder acid in this case than your sulfuric acid. That is because if you use a stronger acid like sulfuric acid, the sulfuric acid itself oxidizes this iodine, that is hydrogen iodide, to get you I2, iodine instead of hydrogen iodide. Hence, a milder acid is used, that is your phosphoric acid, when compared to your sulfuric acid. So the next method we are going to discuss is your Darzon's process. Very important, it's a named reaction, and it is also very important with respect to preparation of haloalkane from alcohol. Let us see what is the reaction. Alcohol reacts with thionyl chloride in presence of pyridine. Pyridine is an organic base. It has a amine group in it. So pyridine, it's a organic base in nature. Products are, you get chloroalkane, that is ethyl chloride, plus sulfur dioxide, it's a gas, plus HCl, which is also a gas. So this is the reaction. You get your chloroalkane from this method. Darzon's process, remember the reagent, thionyl chloride in presence of pyridine, it's an organic base which converts your alcohol into your chloroalkane. Remember here only chloroalkanes are prepared. The advantage of this method is this is the best method to convert your alcohols into haloalkanes. That is because the other two byproducts which you obtained in this reaction, that is sulfur dioxide agirbodu athwa HCl agirbodu, it is gas in nature, that is it's gaseous in nature. This is liquid in nature. As a result, these two escape from the reaction mixture and the only thing you obtain from this reaction is your haloalkane. That is, ಈ ಎರಡು ಬೈ ಪ್ರಾಡಕ್ಟ್ ನ ಸಪರೇಟ್ ಮಾಡೋ ಅಂತ ಗೋಜಿಗೆ ಹೋಗಬೇಕಿಲ್ಲ. ದಟ್ ಇಸ್ ಬಿಕಾಸ್ ಈ ಎರಡು ಗ್ಯಾಸಸ್ ದೇ ವಿಲ್ ಎಸ್ಕೇಪ್ ಫ್ರಮ್ ದಿ ರಿಯಾಕ್ಷನ್ ಮಿಕ್ಸ್ಚರ್, ಉಳ್ಕೊಳ್ಳೋದು ಬರೀ ನಿಮ್ಮ ಕ್ಲೋರೋ ಆಲ್ಕೇನ್ ಉಳ್ಕೊಳ್ಳುತ್ತೆ. ಅದೇ ಬೇರೆ ಮೆಥಡ್ಸ್ ನ ತಗೊಂಡ್ರೆ ಅದರಲ್ಲಿ ಬೈ ಪ್ರಾಡಕ್ಟ್ಸ್ ತುಂಬಾನೇ ಇರೋದ್ರಿಂದ ಅದನ್ನ ಸಪರೇಟ್ ಮಾಡಿ ನಮಗ್ ಬೇಕಾಗಿರುವಂತ ಪ್ರಾಡಕ್ಟ್ ನ ತಗೊಳ್ಳೋದಕ್ಕೆ ಇಟ್ ವಿಲ್ ಬಿ ಅ ಟಿಡಿಯಸ್ ಪ್ರಾಸೆಸ್. ಬೇರೆ ಬೇರೆ ಪ್ರಾಸೆಸ್ ನ ಇನ್ವಾಲ್ವ್ ಮಾಡಿ ನಮಗ್ ಬೇಕಾಗಿರೋ ಪ್ರಾಡಕ್ಟ್ ನ ನಾವು ತಗೋಬೇಕಾಗುತ್ತೆ. ಅಡ್ವಾಂಟೇಜ್ ಇಸ್ ದಟ್ both the byproducts are gases, hence desired product is obtained directly without employing any separation techniques. Separation techniques ಬಗ್ಗೆ ನಿಮ್ ಫಸ್ಟ್ PUC ಅಲ್ಲಿ ಓದಿದಿರಾ, ಕ್ರೊಮ್ಯಾಟೋಗ್ರಫಿ, ಡಿಸ್ಟಿಲೇಷನ್ ಎಕ್ಸೆಟ್ರಾ. ಆ ಸೆಪರೇಷನ್ ಟೆಕ್ನಿಕ್ಸ್ ನ ನಿಮಗೆ ಇಲ್ಲಿ ಯೂಸ್ ಮಾಡೋ ಅವಶ್ಯಕತೆ ಇಲ್ಲ, ಯಾಕಂದ್ರೆ ಎರಡು ಗ್ಯಾಸಸ್ ನಮ್ಮ ಪ್ರಾಡಕ್ಟ್ ಈಸಿಯಾಗಿ ಸಿಗುತ್ತೆ. So that's the advantage of this method. There is also disadvantages in this method. ಏನು disadvantage ಅಂದ್ರೆ you can only prepare your chloroalkane from this method. That is, you can neither prepare your bromoalkane nor your iodoalkane from this method. ಬರೀ chloroalkanes ಮಾತ್ರ ಬರುತ್ತೆ, ಇನ್ ಯಾವ haloalkane ಈ ಮೆಥಡ್ ಇಂದ ಪ್ರಿಪೇರ್ ಮಾಡೋದಕ್ಕೆ ಸಾಧ್ಯ ಇಲ್ಲ. So that is one of the disadvantage of this. Another information I have to give you here, it is pyridine. Pyridine organic base. It's an organic base. ಏನಕ್ಕೆ pyridine ಯೂಸ್ ಮಾಡ್ತೀವಿ ಅಂದ್ರೆ ಇಲ್ಲಿ HCl is a gas. Already I have told you that it will escape from the reaction mixture. ಅಕಸ್ಮಾತ್ ಏನಾದರೂ ಈ HCl ಗ್ಯಾಸು ಸಾಲ್ಯುಬಿಲಿಟಿ ಜಾಸ್ತಿ ಇರೋದ್ರಿಂದ ಅಕಸ್ಮಾತ್ ನಮ್ಮ ರಿಯಾಕ್ಷನ್ ಮಿಕ್ಸ್ಚರ್ ಅಲ್ಲಿ ಉಳ್ಕೊಂಡಿದ್ರೆ ಈ ನಮ್ಮ ಪಿರಿಡಿನ್ ಬೇಸು ಈ HCl ಗ್ಯಾಸ್ ಅನ್ನ ನ್ಯೂಟ್ರಲೈಸ್ ಮಾಡುತ್ತೆ. ಯಾಕಂದ್ರೆ HCl ಇಟ್ಸ್ ಅನ್ ಆಸಿಡ್, your pyridine is a base. ಅಕಸ್ಮಾತ್ ರಿಮೆಂಬರ್ HCl ಸಾಲ್ಯುಬಿಲಿಟಿ ಇಸ್ ಹೈ, ಸೊ ಹಾಗಾಗಿ HCl ಸಾಲ್ಯುಬಿಲಿಟಿ ಅಕಸ್ಮಾತ್ ಇನ್ನು ಒಂದು 3-4% ಅಷ್ಟು ನಿಮ್ಮ ರಿಯಾಕ್ಷನ್ ಮಿಕ್ಸ್ಚರ್ ಅಲ್ಲಿ ಉಳ್ಕೊಂಡಿದ್ರೆ ಅದನ್ನ ನ್ಯೂಟ್ರಲೈಸ್ ಮಾಡಕ್ಕೆ ಯು ವಿಲ್ ಬಿ ಆಡಿಂಗ್ ದಿಸ್ ಆರ್ಗ್ಯಾನಿಕ್ ಬೇಸ್, ಅ ಮೈಲ್ಡ್ ಬೇಸ್ pyridine which neutralizes this HCl acid. ಸೊ ಹಾಗಾಗಿ pyridine ಬೇಸ್ದು ಏನ್ ರೋಲ್ ಅಂತ ಕೇಳಿದ್ರೆ ಇಟ್ ಇಸ್ ನ್ಯೂಟ್ರಲೈಸಿಂಗ್ ದಿ ಲೆಫ್ಟ್ ಓವರ್ HCl gas in your reaction mixture. So that's completely about your Darzon's process. Very important process of very important as well as very profitable process to get your haloalkane from this alcohols. So the third method and the last method wherein you prepare haloalkanes from your alcohols is through phosphorus halides. Either it is pentahalide or trihalides. Phosphorus pentahalides and trihalides. So let us directly take your examples for this reaction because the general reaction I have written here. So directly examples na tagondu explain ಮಾಡ್ತೀನಿ. So this is the third method wherein you can use phosphorus pentahalides as phosphorus trihalides to prepare your respective haloalkane. That is either your chloroalkane or your bromoalkane or your iodoalkane. Coming to the first example, these two examples wherein you prepare your chloroalkanes, chloroethane from your phosphorus pentachloride and phosphorus trichloride. Just react your alcohol with your phosphorus pentachloride or phosphorus trichloride, you get your respective chloroalkane. That is your chloroethane. That is because we have taken ethanol here, so you get respective chloroethane as your product. Coming to your next phosphorus halide, this is your phosphorus pentachloride and trichloride. It is stable in room temperature. So PCl5 as well as PCl3 is more stable in your room temperature. It's just like your reagent put in a reagent bottle. You can use it from your reagent bottles. Just like HCl. PCl5 ಮತ್ತೆ PCl3 reagent bottle ಇಂದಾನೆ ಡೈರೆಕ್ಟ್ ಆಗಿ ನಾವು ಯೂಸ್ ಮಾಡಬಹುದು since it is stable in your room temperature. But PBr3 ಮತ್ತೆ PI3 ಆ ತರ ಅಲ್ಲ. ಈ PCl5 ಮತ್ತೆ PCl3 ತರ ಅಲ್ಲ. That is because PBr3 ಮತ್ತೆ PI3 ಗೆ more steric hindrance ಇರುತ್ತೆ. ಹಾಗಾಗಿ room temperature ಅಲ್ಲಿ it cannot be prepared and stored. ಅಂದ್ರೆ it is highly unstable at your room temperature. Reason ಕೇಳಿದ್ರೆ Br ಮತ್ತೆ I size ಅಲ್ಲಿ more larger than your Cl. ಅದರಲ್ಲೂ 3 Br 3 I ಇರಬೇಕು ಫಾಸ್ಫರಸ್ಗೆ. ಹಾಗಾಗಿ ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್ ಜಾಸ್ತಿ ಆಗುತ್ತೆ, hence it is unstable. I think you have heard the word steric hindrance. So steric hindrance ಜಾಸ್ತಿ ಇರೋದ್ರಿಂದ ಈ PBr3 ಮತ್ತೆ PI3 it cannot be prepared, stored in a bottle and added to your reaction mixture. ಹಾಗಾಗಿ ಅದನ್ನ ನಾವು again in situ preparation ಮಾಡಬೇಕು. ನಿಮ್ಮ HBr ಮತ್ತೆ HI ಹೇಗೆ ಪ್ರಿಪೇರ್ ಮಾಡಿ ಇನ್ಸಿಟು ಪ್ರಿಪೇರ್ ಮಾಡಿ ರಿಯಾಕ್ಷನ್ ಮಾಡ್ತೀವೋ ಹಾಗೆ ಇಲ್ಲಿ PBr ಮತ್ತೆ PI3 ನ ಪ್ರಿಪೇರ್ ಮಾಡಬೇಕು. HBr ಮತ್ತೆ HI ಅಲ್ಲಿ ಯಾಕೆ ಅನ್ಸ್ಟೇಬಲ್ ಅಂತ ರೀಸನ್ ಕೇಳಿದ್ರೆ ದಟ್ ಇಸ್ ಬಿಕಾಸ್ ಅದ್ರದ್ದು ಡಿಸೋಸಿಯೇಷನ್ ಎಂಥಾಲ್ಪಿ ಆಫ್ ದಟ್ ಬಾಂಡ್ ಇಸ್ ವೆರಿ ಲೋ. ಅಂದ್ರೆ ರೂಮ್ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ ಆ ಬಾಂಡ್ ಬ್ರೇಕ್ ಆಗ್ಬಿಡುತ್ತೆ. ಹಾಗಾಗಿ HI ಮತ್ತೆ HBr ಅನ್ಸ್ಟೇಬಲ್ ಅಟ್ ರೂಮ್ ಟೆಂಪರೇಚರ್. ಇವೆರಡು ಯಾಕೆ ರೂಮ್ ಟೆಂಪರೇಚರ್ ಅಲ್ಲಿ ಅನ್ಸ್ಟೇಬಲ್ ಅಂದ್ರೆ ದಟ್ ಇಸ್ ಡ್ಯೂ ಟು ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್. ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್ ಅಂದ್ರೆ ಇಷ್ಟೇ. ಒಂದು ಎಕ್ಸಾಂಪಲ್ ತಗೊಳ್ಳೋದಾದ್ರೆ ಒಂದ್ ಬೆಂಚಲ್ಲಿ 5 ಜನ ಕೂರ್ಬೋದು ಅಂದ್ರೆ ಒಬ್ಬ 6ನೇವನು 7ನೇವನು ಬಂದು ಕುಳಿತುಕೊಳ್ತಾ ಏನಾಗುತ್ತೆ ದಟ್ ವಿಲ್ ಬಿ ಅನ್ಸ್ಟೇಬಲ್ ಇನ್ ನೇಚರ್, ಕುತ್ಕೊಳ್ಳಕ್ ಆಗೋದಿಲ್ಲ. ಸೊ ದಟ್ ಇಸ್ ನಥಿಂಗ್ ಬಟ್ ಯೋರ್ ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್. 5 ಜನ ಕುತ್ಕೋಬಹುದು ಮ್ಯಾಕ್ಸಿಮಮ್ ಕೆಪಾಸಿಟಿ. 6ನೇವನು ಕುತ್ಕೊಂಡ್ರೆ ಏನಾಗ್ತಾನೆ, ಸೊ ಜಾಗ ಸಾಕಾಗೋದಿಲ್ಲ. ದೇರ್ ವಿಲ್ ಬಿ ಅ ಕ್ರೌಡಿಂಗ್ ಇನ್ ದಿಯರ್ ಬೆಂಚಸ್. ಆ ಕ್ರೌಡಿಂಗ್ ನ ಓವರ್ ಕ್ರೌಡಿಂಗ್ ನ ಏನಂತ ಕರಿತೀವಿ ಅಂದ್ರೆ ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್ ಅಂತ ಕರಿತೀವಿ. ಯಾವ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಅಲ್ಲಿ ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್ ಇರುತ್ತೋ ಆ ಮಾಲಿಕ್ಯೂಲ್ಸ್ ಸ್ಟೆಬಿಲಿಟಿ, ಆ ಮಾಲಿಕ್ಯೂಲ್ಸಿನ ಸ್ಟೆಬಿಲಿಟಿ ಕಡಿಮೆ ಆಗ್ತಾ ಹೋಗುತ್ತೆ. ಸೊ ಹಾಗಾಗಿ PBr3 PI3 ದೇ ಆರ್ ಅನ್ಸ್ಟೇಬಲ್ ಡ್ಯೂ ಟು ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್. HBr HI ಅನ್ಸ್ಟೇಬಲ್ ಡ್ಯೂ ಟು ಲೋ ಡಿಸೋಸಿಯೇಷನ್ ಎಂಥಾಲ್ಪಿ. ಈಸಿಯಾಗಿ ಡಿಸೋಸಿಯೇಟ್ ಆಗ್ಬಿಡುತ್ತೆ ರೂಮ್ ಟೆಂಪರೇಚರ್ ಅಲ್ಲೇ. ಹಾಗಾಗಿ ಅವೆರಡು ಅನ್ಸ್ಟೇಬಲ್. ಇವೆರಡಕ್ಕೆ ಅನ್ಸ್ಟೆಬಿಲಿಟಿ ರೀಸನ್ ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್. ಸೊ ಹಾಗಾಗಿ ಇಲ್ಲೂ ಅಷ್ಟೇ PBr3 ನ ಯು ಹ್ಯಾವ್ ಟು ಪ್ರಿಪೇರ್ ಇನ್ ಸಿಟು. ದಿಸ್ ಇಸ್ ಯೋರ್ ಇನ್ ಸಿಟು ಪ್ರಿಪರೇಷನ್ ರಿಯಾಕ್ಷನ್. ಇನ್ ಸಿಟು ಆಗ್ಲೇ ಹೇಳಿದೀನಿ ಇನ್ ಸಿಟು ಅಂದ್ರೆ ಏನು ಅಂತ. ಇನ್ಸೈಡ್ ದಿ ಸಿಚುವೇಶನ್ ಇಟ್ ಸೆಲ್ಫ್ ಯೂಸಿಂಗ್ ಸಮ್ ರಿಯೇಜೆಂಟ್ ಯು ಪ್ರಿಪೇರ್ ಯೋರ್ ರಿಕ್ವೈರ್ಡ್ ರಿಯೇಜೆಂಟ್. ಏನದು ಹೇಗೆ ಪ್ರಿಪೇರ್ ಮಾಡ್ತೀರಾ, ರೆಡ್ ಫಾಸ್ಫರಸ್ ತಗೋಬೇಕು. ದಿಸ್ ಇಸ್ ಯೋರ್ ರೆಡ್ ಫಾಸ್ಫರಸ್. I think you know there are 2 allotropic forms of phosphorus, red phosphorus ಮತ್ತೆ white phosphorus. So ಅದರಲ್ಲಿ red phosphorus ತಗೋಬೇಕು. React it with bromine, liquid bromine to get your PBr3 in situ. ಈ PBr3 produce ಆಗಿರೋದು, this is your PBr3 which reacts with your alcohol to get your bromoalkane. So ಹೀಗೆ PBr3 ನ in situ prepare ಮಾಡಬೇಕು. ಮ್ಯಾಮ್ PBr5 ಇಲ್ವಾ? I am telling you that PBr3 itself is sterically hindered. PBr5 ತಗೊಂಡ್ರೆ ಇಟ್ ಇಸ್ ಸ್ಟಿಲ್ ಮೋರ್ ಸ್ಟೀರಿಕಲಿ ಹಿಂಡರ್. ಎಷ್ಟು ಹಿಂಡ್ರೆನ್ಸ್ ಇರುತ್ತೆ ಅಂದ್ರೆ ದಿ ಮಾಲಿಕ್ಯೂಲ್ ಡಸಂಟ್ ಎಕ್ಸಿಸ್ಟ್. PBr5 ಡಸಂಟ್ ಎಕ್ಸಿಸ್ಟ್. ದ ರೀಸನ್ ಇಸ್ ಸ್ಟೀರಿಕ್ ಹಿಂಡ್ರೆನ್ಸ್. ಅದೇ ತರ PI3 ನೂ ಅಷ್ಟೇ, ಇಟ್ ಶುಡ್ ಬಿ ಪ್ರಿಪೇರ್ಡ್ ಇನ್ ಸಿಟು. ದಟ್ ಇಸ್ ಯು ಆರ್ ಯೂಸಿಂಗ್ ಸಮ್ ರಿಯೇಜೆಂಟ್ ಟು ಪ್ರಿಪೇರ್ ಇಟ್ ಇನ್ ಸಿಟು. ದಿಸ್ PI3 ರಿಯಾಕ್ಟ್ಸ್ ವಿತ್ ಯೋರ್ ಆಲ್ಕೋಹಾಲ್ ಟು ಗೆಟ್ ಯೋರ್ ಅಯೋಡೋಆಲ್ಕೇನ್. ಈ ಅಯೋಡೋಆಲ್ಕೇನ್ ಬರುತ್ತೆ. ಹೇಗೆ ಪ್ರಿಪೇರ್ ಮಾಡ್ತೀವಿ, ಅಗೇನ್ ರೆಡ್ ಫಾಸ್ಫರಸ್ ತಗೋಬೇಕು. ರಿಯಾಕ್ಟೆಡ್ ವಿತ್ iodine to get your PI3. This PI3 in situ is prepared to give you it reacts with your alcohol to get you your iodoalkane as the product. So illo ashte ನೀವು ಕೇಳಬಹುದು PI5 ಇಲ್ವಾ ಅಂತ. So I think you can imagine how I is big. I5 atoms phosphorus ಸುತ್ತ ಬಂದ್ರೆ highly steric hindrance ಇರುತ್ತೆ. ಹಾಗಾಗಿ PI5 it doesn't exist. So the only pentahalide that exists for your phosphorus atom is phosphorus pentachloride. In ಯಾವುದೂನುವೆ you don't have your pentahalides. So phosphorus pentahalide, that is only chloro, not for your bromo, not for your iodo. The reason behind is your steric hindrance. Agla explain ಮಾಡಿದೀನಿ what is steric hindrance. Study more about the steric hindrance also. So these are the methods of preparation of your haloalkane from your alcohols. Remember very muchly you should remember what are 3 reagents which are capable of converting your alcohol into your haloalkane. A very commonly asked question, which of the following is your reagent which can convert your alcohol into haloalkane? ಬೇಕಾದಷ್ಟು reagents ಇರುತ್ತೆ, ನಿಮಗೆ ಗೊತ್ತಿರಬೇಕು ಯಾವ reagent ಆಲ್ಕೋಹಾಲ್ ಅನ್ನ haloalkane ಆಗಿ ಕನ್ವರ್ಟ್ ಮಾಡುತ್ತೆ ಅಂತ.